Hey everyone, Professor Ray here doing another question on free fall activity 8. This one is back to the volcano question. Oh no, the dreaded volcano. It's not, it's gonna be okay. It's gonna be all right. The point of this problem really is to help us recognize everything that we've done already in terms of the work on this problem can be used again, right? I can go through and I can solve this problem from scratch, absolutely. But that's kind of not the point. The point of this problem is, hey, let's see if we could break this down and take advantage of everything that we have done previously, right? But let's see, first thing, got my volcano. I'm gonna draw my picture. Here's my picture. Let's see, I'm gonna draw my picture right here for now, right? It fires up at some sort of velocity right there. I'm just gonna say Y and V because as I'm going through these problems, as we've noted, right, it goes up, it hits some sort of max value. We have another interesting point right here when you're at the same height going downwards, and then it hits the ground. The only thing that I'm like really positive and sure of is when I'm down here at the very bottom, I'm traveling at some velocity that's faster, and when I'm doing my y-axis, my coordinate system, right, y is still positive going upwards, and typically we say y equals 0 is right here at the ground level. Right where it hits the ground. A couple other things we could talk about briefly would be, let's see, I'm gonna choose blue. Right here at the top, up here at the top, I could say my velocity is equal to, hopefully you're saying 0 right now, my velocity is equal to 0 right there. I'm gonna do this down here, I'll use this in green. So in the green dot right here, right, I have a velocity that is bigger and downwards. Now the question right here says, what's the velocity of the boulder when it's at the same height, right? So what's the velocity of the boulder when I'm right here at that same height? Turns out, ends up being, if you might remember, let's see, no, we haven't done that activity yet. Anyway, it's going to be exact opposite on the way down, right? Same magnitude, you're at the same height, same magnitude, same speed, one's going to be in the opposite direction. Why? Why? Let me talk about that here well, not very briefly, but at least get you an idea of what's going on here. If I choose those two to be my 2 points, right? This will be the red point and the orange point. Those are the 2 points that I'm going to be analyzing. I start at the red, which means I have a positive velocity up. Right? Here's my positive velocity up. I'll use red right here. So it's just a VT graph. When I get up to the blue, that means that I am right here at rest. I'm right there at rest. Now I can connect these with a straight line, right? The slope of that should be what? I'm in free fall. The slope of velocity tells you about acceleration. The acceleration in free fall is negative 9.8 meters per second squared. Gravity all the time, always. Which means as this thing continues to come back down, this line continues in a straight line. Okay, so let's think about this. If I were to be back at the orange, right, what would the total displacement be? If I start at red and I go up to blue and back down to orange, right, I'm at the same height. Your total displacement is, hopefully you say, 0. That's absolutely true. Absolutely right. Good job. So here we go. This right here is going to be the displacement up. I'll say delta y up. Delta y up right there. Okay, great. Now, if I continue on to the red, if my line has to continue the same, in order for when I hit this orange point, right, would the orange point be right here? No, it couldn't. Notice that the areas of those triangles aren't the same. In order for the displacement to be 0, the area of this bottom triangle has to be the same as the top triangle. And if these have the same hypotenuse right here, the same slope, right? If it has the same slope, that means that in order to get the same area, my height, orange, has to be at the same level as the red. Has to be at the same value as the red. And the time it takes to go up has to equal the time it takes to go back down to reach the same point, right? I'll say this is T down. Right, and T up will equal T down. That's only when you start to reach the same point, right? If you go all the way down, obviously that's not going to be true, right? But now I have a situation where, because the times are the same, the velocities are the same, opposite directions, I end up with displacements that are the same. The displacements add to 0, delta y down. And then what are we going to say? Our conclusion is that v at the red is equal to v on the orange, magnitude, opposite directions. So I come in here. Let's see. It was initially at 39, so it's going to be negative 39 m/s meters per second. Submit that. There we are. Boom. Good deal. Awesome. Okay. So I'm going to now erase this. And we're going to tackle this other guy, but I'm going to tackle it in a specific way. Okay. First way is trying to use that, what we've already done. Okay. Okay. Two graphs. Let me draw the two graphs again one more time. V, Y, T. A, Y, T. Gravity, once again, should be straight, flat, negative. If you don't have that by now, I don't know what to say, right? You just have to remember in free fall, it's gravity. Gravity is constant and it's negative, okay? Velocity here, we already drawn it. I'm going to draw it one more time, but I'm going to draw it for the whole thing, right? So this is for the whole thing, where up here at the top, this would be where red is. Then we have blue would be right here. Orange would be right that same magnitude, opposite direction, and then I'm down here at the green. Right, I want to know the total time. How much time does it take the boulder to reach the ground, given these variables of 1,300 meters and 39 meters per second? The easiest thing, the best thing to do would be able to choose y1 as the red and y2 as the green, because the benefit of that, well, what is the benefit of that? The benefit of that is then the time that we solve for is the total time. It's the total time, right? So there's some things that we can do here that makes this easy. Some things here that might make this a little more difficult, right? I'm looking for total time. I'm looking for total time. I'm going to do this and do my areas here. So there's that area right there. This is going to be my delta Vy. I get delta Vy equals G times T. This is T total, right? Because I'm doing the whole time here. It's all the way to the green. And that means in order to calculate T total, I need to take delta Vy and take that divided by G. This is V2y minus V1y divided by G. I know the value of G, I know the value of V1y, but I don't know the value of V2y. Here's where, if you have your notes, and do quick little new share. New share, let's go to 1D kinematics with free fall, right? Notice this last guy we did, it was on kinematics, right? Sorry, not the kinematics, it was on learning catalytics, but it says like, hey, what is the velocity of the boulder when it hits the ground? If you solve for that, and you have it in your like regular equations, right? Your general equations, there it is. It's there, ready to go. The solution is ready to go to solve for V2y at the end. All you need is all those different variables that we used from rounds 3. Okay, this is where I hope for students to kind of go to, right? Hope for you to go this way. Just like, hey, you know what? We've solved for V2y. I used it this way. I can use all this that I already did, and I don't have to redo all the work. I can use work that I've already done. I can recycle it. And if you're having notes on the exam, if you have things really organized, you're not going to be able to look up everything. You're not going to be able to look up everything for sure. But when you get to some of those problems, just like, hey, you know what? This looks familiar. I can look at this, and it's right here, and I have all my work. I can do my work, and then, hey, you know what? Things work out that way. It pays to be prepared. Pays to do things algebraically. That way you have general solutions. Okay, so that's the way I'll invite you to do that. Otherwise, this guy gets a little more difficult. Let's first try, I've already solved this once going like T up and T down. No, I've lost everything. Oh, man. What a bummer. Okay, well, It won't take me that long to do this. Hopefully, Vy. I'm not going to use this. I'll just do Ay. This guy looks here, so it's not going to look as nice. Delta Vy equals GT. That's true for when I have the total. It's true if I would just go to the up or the down or however, right? I'll get these dots on here to continue to be, I think it was red, blue, orange, and then the green, right? If I want to know the total displacement, if I want to know the time, right? My total displacement here is going to be the height of this negative, right? Because I start here, I go up, go here, go down. My displacement is going to be from here down to the end if I use this as y1 and this is y2. This is your displacement, delta y. Okay, that delta y, what does that correspond to? It corresponds to this little shaded region right here. Bum, 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 bum. Right, that region right there. Okay, now I'm going to do that. It looks like I'm going to have to break this up into a couple different pieces, right? But this right here, this little region right here only gives me this part, this, I got to be careful. This is like an additional like T. This isn't T total. This is only T from volcano to ground, right? So even if I go through this and I solve for this, it's going to be a little more work because I still have to solve for at least T up and take that times 2, right? Because the time up to get to time, like your original part, the same location, that is going to be the same time. So I could solve for that too. So it's somehow I have to solve for 2 times. No matter what, I'm going to have to solve for 2 times. We have done essentially this guy right here, this right here. What's the T up right there? We've done that. We solved for the max height. It's the same sort of process though. So we could solve for that. And then we could solve for the T down because that's T up times T up. And then we get TV times this, right? Golly, there's just no way real around this. There's delta Y1, delta Y2, all right? Add those up, that equals 1300. And then you have to put those guys together. I'll see if I can write that down real quick. That delta Y for the volcano to the ground, that would be V1, right, times T plus 1/2. This is going to be GT squared. You remember doing that before on maybe on the previous question if you solve for that? Because this right here is going to be 1/2 times T times delta Vy, but I don't know how big that is. You come down here, get the area for this little piece that corresponds. You get your delta Vy from the volcano down. It's going to be G times that time, which is the time to go down on the volcano. Substitute that in. This gets your V1T times plus 1/2 GT squared, right? So you can solve for this time if you wanted to. The only thing is this looks like a quadratic equation, and that's ugly, and I don't want to do that. Okay. All right, we'll go that route. It doesn't quite work. It just happens sometimes. I figured that's where it would go, but I just want to kind of show you. Sometimes you go a route and it just doesn't work. How do you know which route to go? You just got to do lots of problems, and you have to figure out which one works, which one doesn't. So we break this up. Here's what we're going to break this up to. We're going to break this up into 2 processes. I'm going to clear this, and I'm going to go over here, right? I have an up, and then a down, up and down. So I'm going to break this up into going up. I'm going to break this up into going down. And you'll see why this is helpful. You'll see why this is helpful. I'm just going to draw all of these, Vy, T, this is up, and this is Vy and T going down. This is Ay and T going down. This is Ay and T going down. But the thing is all of these have the same acceleration graphs. Same acceleration graphs. There we are. Now, if I look at this again, here's my guy. I'm breaking this up into going up and then going down. Okay. So going up, I have an initial velocity V1 that's positive, and I have a final velocity that's 0. Acceleration, and look at that, it's downwards. Perfect, wonderful. Okay, so how about for Vy, for Vy down? For Vy down, I start at the top. All right, so this is up, this is down. I start at the top and I go down, so I start at V equals 0 and I end at some faster over here. See how when we've broken this up this way, we just have 2 really nice triangles to work with, right? So I have this guy here. This is my delta y up. Delta y up is equal to 1/2 times base, which is time up, times my delta vy going up, right? And then of course, if I come down here, have my acceleration right there. This is delta vy, and I get my delta vy equals, what's this going to be? This is going to be time up times g. All right, so if I'm looking for the time up, right, there's my time up. I can use this equation or I can use this equation. If I look at the top one, I have to think, okay, do I know my delta vy? I do, because I know my initial velocity and my final velocity at y1 and y2, right? That's the top. I know the value of a half, but I don't know the y up. I don't know how far it goes. I don't know the max height. So I have to kind of look at the next one. If I'm trying to solve for time, do I know gravity? Yes. Do I know delta vy? Yes. Cool. Awesome. So I can solve for T up right here. T up is equal to delta vy all over g. Wonderful. Wonderful. Okay. And then that, I won't do this quite yet, but what that's going to help us later as well, not just in solving for the time, but we're going to need that to get another little piece. Okay, so now we go through this process over here and we try to do the same thing, right? So here's my delta y down, right? Because now I'm up at the top and I'm going down. So my delta y down is equal to 1/2 times t down times delta vy. Once again, I don't know the delta vy here. So I know I start at 0, but I don't know what this velocity is. So I don't know that delta vy. So I can't quite solve for this, right? Why? Let's look at that one more time. Looking for delta t down. I know 1/2. I know, I don't even know my displacement downwards. Darn it, and I don't know delta vy. So I need 2 other equations to help me out here. Delta vy, we almost always seem to get delta vy from my acceleration graphs, which is true. And there's my delta vy for going down. Delta vy is equal to t down times gravity. So what do? We take that piece right there, delta t times t down, sorry, that's t down times gravity. It got a little sloppy there. I'll fix it when I get up here. Substitute that right up here. And now we get a new equation for delta y down equals 1/2. It's going to be 2 t downs, right? T down squared times gravity. Awesome. But I still don't know y down, which means I need to know what's my max height, right? What is this y right here? It means I have to use this y up equation that I used previously. So what I'm going to do with this one, it's another substitution. There's just lots of substitutions in this problem, which why it might get a little, I won't say overwhelming, but I'm going to take this time up, put that right there. And so I get from here, delta y up is equal to 1/2 times delta vy squared, right? That's delta vy going up, right? All over g. Yeah. Right? Vy over g, that goes up 1/2 delta vy squared. Okay, yeah, everything seems to check out there. Okay, so now that I have that, I can plug that in over there. All right, so here's where I'm just going to start putting in numbers, right? You might prefer this. Okay, so for time up, let's just do that. I get 39, right? Because it's 39. Final minus initial is going to be 0 minus 39. Divide that by negative 9.8, and you get a positive number. So I get 39 divided by 9.81, and I get 3.97. This is equal to 3.97 seconds. That's for time up. You plug that value up into here, right? And you take that times 39, right? Because that's your delta vy times 39. Divide that by 1/2, divide it by 2. Right? And so my delta y is 77.5 meters. So you got to be careful with that one. You have to be a little careful with that one, because that means my delta yd, right? Delta yd, let me put that in green. Delta yd is equal to, that's your total displacement, which is going to be 1,300 plus 77.5 meters. Because you started up here, right? You started at the volcano, which is 1,300 meters. Now, when you get up to the top, you have a displacement. You have a displacement of 77.5. So that means up here, this y1 is 1,377.5 meters. And then when you go all the way down to ground level, you've lost it all. Okay. So from here, we need to solve for time. Let's solve for that time. I'm going to put that right over here. Getting a little squished. I'll put that right here. So I end up with delta y2 all over g times square root equals t down. It's something we've had before. That's another thing in the free fall. We solved this question. I think it was the first problem. What is the time it takes to go down, or what's the speed when it goes down? We had to solve for the time, right? That's another well-known guy here. You start at 0, you drop it. What's the time? It's this guy right here. The only thing is we had to solve for how high we went. So we're going to take this 77.5 plus the 1,300, right? I guess we have my total displacement. Take this times 2. Divide that by 9.81, and then I have to take the square root of that value. Square root, that gets me 16.75 equals 16.75 seconds. All right, now that's not the answer. That's the time to go from the top down. I have to add that 3.97, and I get 20.7 seconds. So if you went through this and you did it all over again, right? Here it is. But the thing is we've drawn the up graphs before. We should have those equations. We've drawn the down ones for this situation where you drop something at rest. You have those equations. As long as you're able to start recognizing, like, hey, these are the pieces that I've done before. Where have I done those pieces, right? Maybe you can start getting to those answers real quick. Now, this is a long problem, right? This is a homework problem. This is not a test problem. Maybe a part of it may be a test problem. But this whole thing right here, no, this is a homework piece right here. All right, everybody, if this was helpful, press that, tap it, pat it, whatever you do, click it. You probably click it. Click that like button.